Excuse me. So today we're going to talk about graphs of equations and so forth. And I think one important, there's a couple different ways to go at this. And so I'll show you the sort of low-tech version to start with. So, what is the graph of an equation? I guess before I even talk about that, I should just briefly review the concept of the Cartesian coordinate plane, right? So, I'll give you an example. So if I put a point here, if I put a point here, if I put a point over here, if I put a point over there, can you tell me what the components are here? Sorry, these are so small. I'm just going 1, 2, 3, 4, 5, 6. So, like this first point, let me call it P1. Since I go 2 over and I go 1, 2, 3, 4 up, the coordinates are what? 2, 4, right? By the way, there is an unfortunate duplication here. The notation 2, 4, it means two different things in mathematics in the US, right? Like, on the one hand, it means that point, 2, 4, but we've also used it to mean the set of x such that 2 is less than x is less than 4, right? So like interval notation and point notation, they're using the same symbol for rather different things. There's just something to be watchful of. There's almost never a danger of confusion between those two things, but it is technically another meaning for that same symbol, Anyway, how about this one? I go -1, -2, 1, 2, 3, 4, 5, 6 over, so we've got what? 6, -2. I'll call that P2. And this guy over here looks at like it's what? P3 is where? We've gone over 2 and up 2. Yeah, -2, 2, right? And how about this one? One, 2, 3, 4. Looks like I got -4, -4 for my P4. So just a reminder, point, quadrant, point 1 is in quadrant what? Yeah, quadrant 1. And for reasons I don't fully understand, we use Roman numerals for the quadrants typically. So like this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4, but Roman numerals, that's 1 less than 5. So anyway, it's just like that. So point 2 is in quadrant 4 in my picture. Point 3 is in quadrant 2. And point 4 is actually in quadrant 3, as I've labeled them. So that's just language we need to be familiar with because, on occasion somebody references quadrants and it's good to know what they're talking about, right? All right, so let's look at an equation. What if we looked at x squared plus y squared equals to 1? how can we understand what this equation is? Actually, does anybody here know what this equation is already? Okay. What's that? Yeah, like what is it on a graph? Any idea? Let's figure it out, right? So what we can do is we can make a plot of points. We can put x and we can put y. Now, we can do algebra to solve for y, right? So what's y going to be equal to? Y squared is 1 minus x squared, right? So therefore, looks to me like y is plus or minus the square root of 1 minus x squared. I'm pretty sure all the algebra steps I just made are algebra steps that you've seen before, but maybe you haven't used them to do this, right? That's okay. If you don't like this, you could just work it out point by point. But that is how you solve for y here. The trouble is we could either have plus or minus, right? Okay, so so let's start thinking about it. Like, what kind of values can we put in for x that we're going to get like a real y for? What if I put x equal to 2? What would happen? What if I put x equals to 2? What would happen? I get 4 plus y squared equals to 1, right? Close. Square root of what? Negative 3, yeah. I mean, we get y squared equals to 1 minus 4, which is minus 3. This has no real solutions, right? So, like x equals to 2 is not going to give us any points in the xy plane where the equation's true, right? So we shouldn't put 2 on our table of values. It's not interesting, you know? So if you start thinking about this formula, you'll realize that whatever we put in for x, it can't be make x squared bigger than 1, right? Because if it did, then we end up with the same problem again. So long story short, you could start at minus 1. And then we could put in like minus a half for x, put in 0, put in half again, put in 1. I mean, that's a pretty good table of a pretty good set of values here to figure out what this thing looks like. I'm just trying to explain to you my thinking why I didn't start at like minus 3 or include 2 or something. I know they're not interesting because there's no solutions in those cases. You're like, this plus or minus thing you did with the square root, I don't care for it. So did we need to do that? Not absolutely. If you make this table of values, you could also like attack it one at a time, right? Like minus x equals minus 1. That would give me what? That would give me 1 plus y squared equals to 1. And that tells me y squared is equal to 0, right? Which would give me the solution y is what? 0, right? 2? Oh, no. Subtract 1 from both sides. Y squared is equal to 0. So, like plugging in minus 1, I can see y is 0. If you weren't able to do the algebra I did, you should still be able to get that by just plugging the number into the equation directly, right? So maybe that's better. Maybe I should just say, since you guys are balking, and you're like, y such that x squared plus y squared equals to 1. Let's just say that. And we'll forget about that formula, which you guys don't know how to derive. Since you're not comfortable with that, let me make it go away. You know? Adios, muchachos. See here, there, 1. What happens when we plug in minus 0.5? What's 0.5 minus 0.5 squared plus y squared equal to 1, right? So that's y squared equals to 1 minus 0.25, which is 0.75. So how can we have y squared equal to 0.75? That means that y is plus or minus the square root of 0.75. In other words, y is equal to plus or minus 0.86 approximately. Because everybody knows that the square root of 0.75 is about 0.86, right? That's a joke. I just know it because I did it yesterday. So, yeah, plus or minus 0.86, approximately speaking. And by the way, while we're at it, what if we had done 1 instead of minus 1? Would that have changed the first calculation? It wouldn't have changed it a bit, because when we square 1, we'd still get 1. So that first math would still lead us to the same thing. In other words, there's a symmetry here. Minus 1 and 1 both go to 0. The minus 0.5 and the 0.5 both go to plus or minus 0.86. One more to do. What if we plug in x equals to 0? We get what? We get y squared equals to 1. Right? So y is equal to plus or minus the square root of 1, also known as y is plus or minus 1. All right, so there you go. We filled out a table of values. We plugged in x values. We figured out the y values have to be. And now we can use these to plot the graph of this equation. What are the points which are on the graph? Let me list them for you. We've got minus 1, 0. We've got minus 0.5, minus 0.86. But we also have minus 0.5 plus 0.86. And we also have 0, 1. We have 0, minus 1. We have 0.5 minus 0.86. And finally 0.5 plus 0.86. There's an explicit list. We have found 8 points on this mystery graph. Okay? Now if I had a, if I were you, and if I gave this kind of problem on a test, where I actually expected you to, make a table of values and plot the graph using this method, I would provide a graph paper in like the place where you write your answer, because I don't want to watch people freehand like graphs. No, I'm not interested. I don't want to grade that. So what I'm doing, I have extra work to do here, right? Because this chalkboard did not come with a graph built in, did it? So that part of the difficulty of the problem is removed for you, because I would give you like a little graph to work on if I was to ask this question. But let's see here. I'm going to make minus 1 down here. I'm going to make, let's see here, I'll try to use 1 up here. I'll try to do it somewhat carefully. So 1's over here. Minus 1's over here. So, all right, let me label some points. This point here would be what? 0, 1. This point over here would be 1, 0. This guy over here would be minus 1, 0. This one down here would be 0, minus 1. So those are 4 of my points. And where are the other 2? They come in pairs that are like symmetric across the x-axis, right? Like a half plus or minus 0.86. So halfway, and then 0.86 is like it's like up here somewhere. So roughly speaking, here and here, this is my point, 0.5, 0.86. Down here, 0.5 minus 0.86. And the same song and dance over here. Minus 0.5, 0.86. And then on the other side, minus 0.5, minus 0.86. And I think that should have been a little bit lower. Let me make the dots bigger. What is it?
Circle.
It's a circle. Yes, we have a winner. Up to the limits of my artistry, it's a circle, yeah. And we can actually understand that through some simple argument. What's the distance formula? What's the distance from the origin to xy? If I was to go back over here and erase the evidence of this part of class and instead draw you a picture and I was to say, what's the distance from the origin out to that point, what would you tell me? What's the length of that line? You do what? You imagine like a little right triangle, right? This distance is x. This distance is y. So this is the square root of x squared plus y squared, right? And this formula still makes sense if the point is in quadrants 2, 3, or 4. Doesn't care about the signs. I mean, that's the distance formula for a point from the origin. We take the square root of the sums of the squares. That gives us the distance from the origin. So the distance from 0, 0 to xy is the square root of x squared plus y squared, right? So what does this equation really say? This says, if we think about it, the square root of x squared plus y squared squared, right, equals 1. So it's entirely logically equivalent to just saying the square root of x squared plus y squared equals to 1, because everything in question here is positive, so nothing is lost by taking the square root of the equation, essentially. I mean, I don't even need this per se. I'm just trying to tell you that this equation and this equation are the same equation. And what does this equation say? Geometrically, that says the distance from the origin to the point xy is 1. So the solution to this equation is the set of all points xy, which are distance 1 from the origin. That's how we define a circle, like geometrically. We say it's a set of points that are equal distance from a center point. No? No one ever defined a circle for you?
Yeah, but I'm saying I don't get it.
The last part of what I'm saying is like an extra commentary. When we drew that circle after you told me it's a circle, that was the end of the part of the test question. Past this, I'm just trying to explain to you why this is not surprising in terms of equations. Another example? Yeah. Oh, sure. We could do like y equals to 3x plus 2. Here's x. You might want to, yeah. So this one is a little bit easier because we've already got y, right? So all we got to do is plug in x. And then we get the y value, right? So I'll do like minus 2, minus 1, 0. 1, 2. That should probably be enough for us here. So what do we get for, let's see, 3 minus 2 plus 2, which is what? Negative, yeah, negative 6 plus 2, which with minus 4. Minus 4, very good. And then we got what? We got 3 times minus 1 plus 2, which is? Negative 1. Plug in 0, we get 2. What happens when we plug in 1? I got a 5. I plug in 2, what do I get? Right. So, let's see here, my see, I need something. I need to go from like minus 4. I think if I make that the scale on my axes, I should be able to plot everything I need. By the way, that's like a lot of trouble in your science classes, right? That's part of the difficulty of being a good lab student is like choosing the right set of, like the right scale for each axis, right? Like I taught physics for a few years, and one of the things I've seen in the vast majority of engineering students I ever taught, most of them don't know how to make a graph. Like they have data and they will just take the whole graph paper and they will shove everything down into like a little postage stamp. They've got a whole paper to work with, but they don't choose their scale correctly so that they can actually see what they're doing. And so it's something that's always worth trying to take a second to think about is like, what should my numbers be such that I capture the information I'm looking at, you know, and I can get everything sort of on the paper. In this one, that's why I put the minus 4 down here, because I looked at this, I'm like, okay, minus 4 is the smallest thing I'm going to plot y-wise, and 8 is like the biggest thing, so I know I need to be able to go from minus 4 to 8. That's why I made the graph like that. That's actually kind of a generally difficult problem to think through, and I think a lot of people need to work on that, and sometimes I do too. Let's see here, especially if I'm hurrying. Okay, so minus 2, we got a what? Minus 4. That's that first point, right? And then when we get to minus 1, we're at minus 1, which is somewhere in here, right? And then at 0, we're at 2, right? And then when we get to 1, we're at 5. And when we get to 2, we're all the way up to 8. So what do we got? What's that? This is a line, right? It's a line with slope 3 and y-intercept 2, right? Y equals mx plus v. See, m equals to 3, v equals to 2. But if you didn't remember that, then we can make a table of values and find that it was a line, right, if we have some time. Now, you're allowed a graphing calculator for the test, right? So in principle, you can replace the table of values with using the graphing calculator to see what it looks like, right? And you could get the values for your table from the graphing calculator if you were so inclined. I don't know. But there is, I mean, this is really not the smartest way to make graphs, right? This is very, very time consuming. And we do have a lot of technology to help us, right? So if we use the technology wisely, we can quickly visualize a wide variety of equations without so much work, right? So let me show you how you can do that, in part to help with your homework, but also just because it's a good life skill to have to know how to use some math software online. Yep.
Where did you say we can get the graphing calculators from here?
Oh, the math, it's the Math Help Center or the Math Learning Center. I've forgotten the name of it, but it's downstairs, like close to the 126F classroom. So it's like you just go down to the first floor, and at the end of the hallway, you'll see it. You should find it. It's like, I think it's that away.
Okay.
Yeah. My office is sort of in there, so. Well, my office is like the next room over, which is a classroom. Technically, my office is kind of inside a classroom. There's two offices inside this classroom at the back. I mean, it's closed off, right? So like, sometimes I'll be making a video inside my office while somebody else is giving a lecture outside. I'm like, I hope I'm not disturbing them. But anyway. So yes, you can get a graphing calculator from there, but you know, by and large, let me just tell you, to be honest, I will not ask a question on the test which specifically forces you to use a graphing calculator. I don't think it's a good thing to do for you. I may ask questions where a graphing calculator is helpful if you know what you're doing. However, I still expect you to show your work. So like a graphing calculator finding you the answer still wouldn't get you full credit. It would just get you partial credit at best, right? So, I mean, get a graphing calculator if you think it's going to help you, but I would also be perfectly happy with you just using this with understanding. That would be an equally good solution in my book, personally. This is, have I showed you guys this yet? I don't think I have. This is www.desmos, D-E-S-M-O-S. Which I'm sure means something. I don't know what it means, but I'm sure it means something. But it's free, which is good, right? Like I spent enough on my access code for my math lab already, right? I hear you. If I can pull this. Take that. Check it out. So it took us like what, 10 minutes? And if we use technology, we can do it in 10 seconds. There it is, unit circle. And cool thing here is you could even do something like put a variable in. It allows you to quickly add a slider. So I put A as a slider, and then I can adjust it and see what happens if I adjust that parameter. See, if A is negative, there's no solution, right? Because if you had x squared plus y squared equals to minus a number, think about it. There's no way you can solve that, right? So there you go. And you can look at other stuff like, I don't know, what if you put a 2 here? What happens? Oh, you get an ellipse, right? And if you change it, then it makes the ellipse bigger or smaller. What happens if you change that 2 to minus 2? What happens then? Oh, look, you get a hyperbola. And it's a hyperbola which opens sideways, except when A becomes negative, it opens vertically. So you get hyperbolas both ways, like these and like these. I don't know. You could do other stuff, like how about x, y equals to 1? Well, that's a hyperbola which opens like that way, you know? And we could do other stuff, like here's some. I showed the other class this, x cubed plus y cubed equal to 1. That one's funny. I don't remember that happening. Oh, I know what it is. I need to put absolute values in. So absolute value is just the vertical pipe symbol. So there's x cubed plus y cubed equal to 1. I'm going to get rid of this thing. Let me put, you can do more than one at a time too. Like here's the unit circle. Check that out, right? Here, how about let's do this. Absolute value of x to the p power. We'll add a slider for that. Plus absolute value y to the p power, and we'll set that equal to 1. Let's see what happens, right? Well, that's kind of funny, right? See the purple one? That's p equals to 1. I'll make p step from like 1 to 10 or something, I guess. And I'll do it in steps of 0.1. All right. So you can visualize different cases all at once, right? Like this is absolute value of x to the p, absolute value of y to the p equal to 1. See the purple thing? So it becomes like a diamond at the smallest. It blows out to a circle like what we're used to. And then as p gets really, really large, it's going to actually become like the unit square. For what it's worth, mathematicians say that all these things are circles because these are all the set of points that are the same distance from the origin. However, mathematicians' definition of distance is different than the one I have covered up with this whiteboard. Like the distance that we use in here is the Euclidean distance. It's the standard Euclidean distance. But there are other notions. So, I mean, there are mathematicians who would say that the square is the circle. I mean, so I tried to explain this to a philosopher once. He said it's absurd as squaring the circle. And I was like, but the thing is, for us, a square could be a circle in mathematics. It's been the case for about 200 years. He did not want to hear me. I don't know. Like, if you try to tell philosophers they're wrong and they have the wrong mindset, like they will not listen to you. Especially if you're a student and they feel like you haven't done your homework, stuff like that. That would frighten me. Anyway, is this enough? We could do other ones. You guys give me any equation you like. X to the fourth, how about plus 5xy squared minus 16 equals to x divided by parentheses x plus 8 times y. There, what's that? I don't know, but apparently it looks like this. Do you want to make this with a table of values? I know I don't, right? But anyway, the bigger picture I'm trying to tell you is you can make almost any shape you want with equations if you're sufficiently clever. I mean, here, check this out. If you want to make like, suppose I want two lines. I want the line y equals x, but I also want the line y equals, come on, minus x. If I want both at the same time, I did the same thing twice, doofus. So this equation, y minus x times y plus x equal to 0, it gets two lines, see, because if you have y equals to x, it solves the equation. If you y equals minus x, it solves the equation. What if I want to make an equation which has the two lines and also a circle? Simple. I just add another factor, which is solved when you're on the unit circle. And I could add another circle somewhere else if we wanted, you know? Like, I don't know, maybe you want to, where do you guys want this next circle to be? You want me to add a hyperbola? I could add a hyperbola if you'd like. Okay. I can tell you're sincere in your desire. See, I often tell students, like, you know, I don't think I've told you guys this yet or not, but there we go. But anyway, you can just keep adding adjoining equations to your heart's content to make whatever kind of pattern you want. You can pretty much make any curve you can think of the solution set to a sufficiently complicated equation. People who do this for a living are called algebraic geometers. But that is definitely something I shouldn't be saying in here. So let me turn this off. This is a temptation. This thing is like, it just makes me want to say things that don't help you with anything particularly, but Hopefully you're relaxed now. I don't know. Let's see here. Any questions about this? I mean, you can use this easily to graph almost anything that you need to graph in your homework. I know in the homework sometimes they have like a graphing tool you have to work with, right? So if that's giving you trouble, you could go over to this and look at it and maybe figure out what's going on or something pretty easily. Anyway, I always share this with students because I think it's very helpful. And with that, I'll put that away. And go on to the next topic, which, if I recall correctly, is functions. And so what is a function? And then correspondingly, what does the graph of a function look like? What's the difference between, say, the graph of an equation versus the graph of a function? How are they related? How are they the same? What can we say? So I need to be a little bit abstract with you here for just a second. To define a function, it's helpful to kind of take a step away from, equations and formulas for a second and just think about sets. So definition. F from A to B, where, actually, I keep doing this. I mean to write something else before that. Let me start it out right. Suppose A and B are sets. So that just means there's some collection of objects, okay? Then F from A to B is a function, all right, with the domain of F equals to A and codomain of F equals to B if for each x in A, the value f of x in B is a single element. So let me draw a picture, just sort of a heuristic picture, but so this we could think of as being A. Over here, we could think of this as being B. F is a function. It takes something in A, and it moves it over to something in B. It's a machine that takes things in A and produces things in B. But the way the machine works is that if you give it a single input, x, you get a single output, f of x. That's it. Now I can say more. I can also talk to you about the range. The range of f is equal to f of x such that x is in the domain of f. In other words, the domain is the set of possible inputs for the function. The range is the set of possible outputs for the function. The codomain is this sort of like larger set where the range has to fit in. And I'll try to explain to you why we even care about such an idea with an explicit example But just here's like a picture, basically like, oh man, so sad. So maybe the range is just this piece right here, right? So like these points not hit by F, right? Outside the range, the points are not mapped to. Let's look at a specific and very silly example. All right. So I'll let A be the set 1, 2, 3. I'll let B be the set cat, dog, Naruto. And I will define a function as follows. F of 1 is cat. F of 2 is dog. F of 3 is cat again. So that's the one way we could define it, just by writing these equations. You could also define the function using like a picture. So like entirely equivalently, you could make 1, 2, 3 this picture. Over here we could write cat, dog, Naruto. And we could picture the function by like little lines that show you the action. Like 1 goes to cat, right? 2 goes to dog, and 3 goes to cat again, right? It's okay for different elements of the domain to go to the same element in the range. Like 2 different elements in the domain can map to the same output. But what we can't have is like f of 1 mapping to cat and dog. Like f of 1 has to be a single thing. It can't be f of 1 is equal to cats and dogs, you know? Like this is not allowed. A function has one output for each input. Okay? Now, so for this silly example, can you tell me what's the domain, what's the codomain, what's the range? By the way, sometimes we abbreviate domain to dom because we get sick of writing domain. What's the domain? What's the codomain? What's the range? The drinking fountain did not give me a sense of assurance that I should drink from it. If I hit the button, it starts squirting a wall. Like, And then I'm like wondering, when's the last time that fountain was actually used? I don't know. Probably when I wet this thing last week, but anyway. So the domain? You can do it. No? Sorry, I'm always, whenever I say you can do it, I'm referencing the I forget what it was, Olympics, where this poor girl broke her ankle, and then her coach shouts at her, "You can do it, you can do it." Like, she's broke her ankle. Like, why you make her go again? She's going to break her ankle, like, for real this time, not just a sprain. But this is held up as, like, an example of greatness. But I just see a mean old man making a little girl break her foot for the sake of spectators. Other people see a great sports moment full of heart. You know, whatever. Sorry, what did you say was?
I never called it codomain.
Oh, well, I know exactly. I think no one's heard of codomain. That's why I'm introducing it here. So the codomain is just whatever this is. So in this context, codomain here is B. The domain is A. It's 1, 2, 3. And the range is what? Cat dog, exactly. So the point is that the codomain can be bigger than the range. That's all. Now, how about a function? Here's another definition for you. A function f from A to B, where both A is a subset of the reals and B is a subset of the reals, is called a function on R. So a function on the real numbers maps some subset of real numbers to some other subset of real numbers. All right? And for this, we can define the graph of such a function to be the set of ordered pairs x comma y such that x is in the domain of the function and y is equal to f of x. So the graph of a function is a set of ordered pairs such that y equals f of x, and x has to be in the domain of the function. So that's a lot like, I mean, that's not so different than the graph of an equation we started with, right? Like, I didn't write this on the board, I think, but what is the definition of a graph of an equation? It's the set of x comma y that when you plug it into the equation, it holds true, right? So I'm telling you the graph of a function is a set of x comma y such that when you plug it into the equation y equals f of x, it holds true. So they're very much related, but there's something special that happens for functions, right? So let me draw a potential graph of a function, and I want you to explain to me why it can't be actually the graph of a function. So I'll say graph of function, question mark. So let's look at it. Suppose I tell you, I've got this function to sell you, and I will give it to you for $1. Why should you reject my sale? I don't have a formula, but here's the picture of the graph. Let me put some numbers in here. Suppose that this is 6, right? And let's suppose that that point is 6 comma, I don't know, 2. And this point here is 6 comma 3. And maybe this point up here is 6 comma 5, right? So those are all elements of the graph of something I'm claiming might be a function. Why is it impossible for this to be the graph of a function? What would it mean if those 3 points were actually on the graph of the function? So I think this is even easy. So look, xy is equal to x comma f of x is how I usually think about it. A point on the graph of a function has the format x comma f of x. So if I want to read off values of the function from the graph, I use this as my guide. So looking at these 3 points, what's f of 6 equal to? Is it 2? Because that's what the lowest point suggests. Is it 3? That's what the middle point suggests. Is it 5? That's what the upper point suggests. See, we would have to have f of 6 equals to 2, f of 6 equals to 3, f of 6 equals to 5. This is forbidden. Right? The very definition of a function is that it outputs a single value. So I can't have a graph which has more than one values for a given input. What I'm trying to explain to you right now is called the vertical line test. The graph of a function has to satisfy the vertical line test. In other words, vertical line test says what? Each vertical line hits at most one point on graph of function. Sorry, my handwriting, it devolves to bad writing at the bottom of the board. Sorry. So here's an example of something that could be a function. It turns out if we were to plot y equals f of x, where f of x was given by 1 over x squared, it looks like a volcano, actually. So this one, does this pass the vertical line test, right? You think about it, right? Any place I can draw a vertical line, I'm just hitting what? 1 point, that's right. So that means that, yes, this will pass the vertical line test. Now I say at most 1 point. Why? Because at the y-axis, does that intersect the function? Not at all, right? And that's okay, because that point is what? It's actually not in the domain of the function. What's the domain of this? X such that what? X not equal to what? What is the forbidden fruit to this function? The one thing it cannot have. An input of? I heard 1. Maybe I misheard. What number can I not put into the formula f of x equals 1 over x squared? Like what one number is going to mess that up? 0, right. So x not equal to 0, that's the domain. If we wanted to write the domain in interval notation, we would do what? You'd say, that's so last week, we don't care about that anymore. Why are you bringing that up? That's a sore memory. Well, I'm sorry, but like interval notation will be with us. This is one of our goals for the course is to understand interval notation. And if you don't understand why this is that, draw the number line. We're excluding 0, right? So on the one side, you've got minus infinity to 0 not included. On the other side, you've got 0 to infinity included. We union those together to get the domain in this case. What's the range for this function? So I've shifted gears. I started out by talking about the idea of a function somewhat abstractly, right? Now I'm talking to you about functions more just about functions of the reals, right? So we can talk about their graphs in the xy plane, and I can make some very specific statements. For example, the domain is basically just all of the x values where you find points on the graph, right? The range, it's all of the y values that the graph covers. That's it. So what y values does this graph cover? Does it cover y minus 1? Can y be minus 1 on the graph? No. Like at this point, like here maybe would be the 0.11 or something, I don't know. Over here you got like minus 1, 1. If you look down here, here's y equals like minus 1. That, well, not quite to scale. I guess it's like minus 0.5, whatever. Anyway, the point is that never intersects that graph. If you look at the formula, this is what? This is greater than 0, right? It can't even be 0. Can you have 1 over x squared equal to 0? No, you can't. You can get really, 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 really close to 0, but you can never get there. So the range in this case is actually 0 not included to infinity. So I need to share with you a custom that I actually just used, which is that we make the domain of f as big as possible when given a formula f of x with no strings attached. So if somebody gives you a formula, f of x equals to blah, and they say, what's the domain? The custom is to give them back the largest possible set of x, which make the formula make sense. But in truth, we can always take that set and make it smaller if the domain makes sense. Like, you could have a function that's like a function of population, right? You might have a formula that makes sense for any possible population. But then because your variable is population, you might say, I'm going to throw out negative population because I don't know what it means to have negative 10 rabbits, you know? And maybe a pet store knows what minus 10 rabbits means, right? Maybe that means they've got 10 on order, but not 10 in the store or something. I don't know. You could give a meaning to minus rabbits if you wanted to, but let me stop talking about negative rabbits and move on to a different example. Was the circle we looked at earlier the graph of a function? Why or not? Is the circle a graph of a function? No, why not? More than one point, right. So circle, we look at this line, right? And we got these 2 points. So it fails the vertical line test. It is not a function. However, you could write a circle as the graph of 2 functions. You could write it as this one and also that one. And those are the things I wrote at the start of class that you guys didn't want to see. Well, I'm putting words in your mouth, but these are the things I wrote at the start of class that made you worry about whether or not I was going to ask you to do the same thing. How about that? That may be more accurate. So the top equation is the graph of the square root of 1 minus x squared. And the bottom equation, that's the graph of the function f of x equals this minus the square root of 1 minus x squared. If you put those two together, you get the whole circle. Each one of those half circles separately satisfies the vertical line test, right? So, and this is kind of generally what happens with an equation, is if you zoom in enough, you can solve and make it into the graph of a function just like locally. But generically speaking, to get the whole thing, you got to have more than one function. All right.